So now let's talk about mixtures of gases. And with that, we need to understand Dalton's law of partial pressures. And basically what Dalton expressed is that, the total pressure is the sum of all the individual partial pressures of gases that makes up the mixture. So we could say that you have a total pressure, and that's just equal to the sum of all the individual partial pressures. So what we see, here, these are what's known as the partial pressures. These are individual pressures for a specific gas, but since now they make up part of the total pressure, that's why they have this slightly different moniker with partial pressure. The other way we can talk about this is more in terms of maybe a percentage. Where we have the partial pressure of a gas, let's say gas 1, is equal to the mole fraction of gas 1 times the total pressure. So here we have the partial pressure of gas 1. We also have the total pressure of the system, and this is known as a mole fraction. So really it's just like a mole percent, but we're not multiplying by 100. So the mole fraction of gas 1 would be moles of gas 1 over then total moles of actual gas. So we have these, three equations that we utilize. We tend to use this last two a little bit more often than the top one. But that's all that Dalton's law is really talking about with mixtures, is that every gas within the mixture has a pressure that's now classified as a partial pressure. And if you sum up those partial pressures, you have the total pressure. And another way to think about that is by this idea of mole fraction, right? Just looking at, kind of the percentage of the gas that makes up the mixture. So let's look at an example of this. So maybe make our numbers a little bit more accurate here with 3 sig figs. So dry air is 78% nitrogen, 21% 1% oxygen and 1% argon by mass. What is the partial pressure of each gas at atmospheric pressure? Or 1 atmosphere. So here we have a mixture of gases. Should have that phase for the argon there. So we should be thinking about, this idea that I can determine the partial pressure of a gas if I know its mole fraction and if I know the total pressure within the system. I know the total pressure is 1 atmosphere. So basically what I need to do here is, first solve for my mole fraction. And then with the mole fraction, I can now solve for the individual pressures of the gases. So I just need to, for this first step, we're going to need to assume, 100 grams total. So that means that we would have, 21 grams of our oxygen. And if we divide by 32, we should get 0.66 moles of our oxygen gas. And we're going to do this for the same procedure for the other gases that are there as well. We have our 78 grams of the nitrogen. Divide by its molar mass of 28. That gives the value of 2.79. And then we want to do the same thing with our argon by taking that 1 gram and dividing by its atomic molar mass of roughly 40. To give us a value of 0.025 moles of argon. So that's the first step, is to get to these mole values, and then these are basically leading to step 1, where we want to get at now the mole fractions for each particular gas that's actually there. So now I can put the mole fractions together. For the oxygen, I take the 0.66 moles and then divide it by the total moles of gas to give us a value of 0.19 for oxygen's mole fraction. And then I can do the same thing for our nitrogen gas. The numerator changes to the 2.79, but the denominator is going to stay the same as the total. And so that's equal to 0.80. And then we can do the same thing for argon as far as this conversion, but realize that the sum of the mole fractions, much like the sum of percentages would equal 100, the sum of these mole fractions should equal 1. So we could just, take and solve for the mole fraction of argon by taking 1 minus our 0.19, which is the O2 mole fraction, and minus 0.8, which is the nitrogen, and we get 0.01 for its mole fraction. So that was step 1, and now we can move to step 2, which is, solving for the pressure of each individual gas. We know the total pressure, we know the mole fraction, and since our total pressure is 1, that really means that these mole fractions are the same as the partial pressure. So for our oxygen gas, we would have, 0.19 as its mole fraction times the 1 atmosphere, or 0.19 atmospheres for our O2. And we want to do the same thing for the nitrogen gas with its mole fraction of 0.8. And then the same thing for our argon gas, which has a 0.01 for its mole fraction. And so we end up with these partial pressures for each one of the gases that makes up the mixture of dry air. 0.19 for our oxygen, 0.80 for our nitrogen, and 0.01 for our argon. So that's one example of using Dalton's law of partial pressures. A common experiment that involves a redox reaction, or a gas evolution reaction, is collecting gas over water. And so this is a common experiment that we run with gaseous types of reactions. It looks like this in terms of the experiment. So if we look at this experiment on the left here, we have our our redox reaction that's occurring. The zinc here is actually undergoing an oxidation. It's becoming +2. And our hydrogens, really our protons from the HCl, are being reduced to hydrogen gas. So we have our reduction, let's get that correct. We have our oxidation with the zinc. We have our reduction with the hydrogen. And so overall, we'll be looking at, a reaction that looks like this for our redox process. And so notice that we're producing hydrogen gas. So the zinc turns out to just simply dissolve. It turns into zinc +2 and goes into solution. And then we have our hydrogen molecules here being produced. And those hydrogen molecules travel up this sealed container down this tube, and the tube actually runs into a container that's submerged within water. And so we can see here we have H2O, and so we have this H2O solution that's below, this is just H2O, and then we have H2O being trapped, and as we produce more and more of the hydrogen gas, right, we are now trapping the hydrogen, or we are collecting the gas over water, right? And so that's where that name of the experiment comes into play, is because that's what we're actually doing. It's collecting gas over water. Now, remember, H2O has a vapor pressure, right? We talked about that notion of vapor pressure already, meaning that with liquids, there's always a certain amount of that liquid actually in the gaseous phase. And so we can see that in terms of we have H2O molecules in this area, as well as having our hydrogen molecules as well. So in this container that we have for this top portion, right, we have here a mixture of gases. Namely, we have hydrogen gas and we have H2O gas. And that is now why we would need to use Dalton's law of partial pressures in this type of experiment. That even though it looks like we're kind of collecting this hydrogen in its pure state, it just so happens that where we're collecting it, there's actually already some gas there in terms of the water vapor, which is directly proportional to the vapor pressure of the H2O. So that means when we're trying to figure out some type of value in terms of the gas that we're collecting, in this case hydrogen gas, that means we'd have to treat it as a mixture of gases before we could solve. So let's look at an example of this. So we have a gas sample weighing 0.523 grams, has basically a volume of 456 milliliters. When collected over water at 30 degrees Celsius and at a pressure of 725 millimeters of mercury. We want to calculate the molecular molar mass for the gas collected. The pressure of H2O here, noting that this is the vapor pressure, is equal to 18 millimeters of mercury at 30 degrees Celsius. So given all that information, we should be able to determine the molar mass of the actual gas. So if I look at that idea, right, this is where I'm trying to go, is this molar mass of the gas. And if I think about my ideal gas law and the information that's given to me here, I would think of this expression, I have a mass of 0.523 grams. I also have a volume of 456 milliliters, and I have a temperature of 30 degrees Celsius. So there's quite a bit that I already know here from my information above, right? R is our constant. And our temperature would be the 30 degrees Celsius plus 273, or 303 Kelvin. And I also have a pressure here, but we need to be careful with this idea of the pressure. This is for a mixture of gases. So my P total is equal to 725 millimeters of mercury. But again, this is a mixture. What I need to figure out is the pressure of the actual gas I'm collecting. And then I can use that in terms of my expression. So there's really two steps here that we need to do. Step one is really this combination of this pressure total and individual pressure. And so there's, Dalton's law. And then once we have that, we can then go up and use our expression and solve for the actual molar mass. So step one, right, is to realize that our pressure total would be really the pressure of the gas that we're interested in plus the pressure of the H2O. And we know that value, right, that was given to us here at the very bottom of the question of 18 millimeters of mercury. Realize it also gives a temperature, and that's important, right? Realize that vapor pressure is temperature dependent. So as I raise temperature, my vapor pressure naturally increases. In order for us to relate these pressures to one another in terms of the experiment that we're doing, we would have to make sure that we're at the same temperature. So the temperature of the reaction is 30 degrees Celsius, right? That's what we're plugging into our ideal gas law. But that also means, in looking at Dalton's application here, that the pressure of H2O must also be at that same temperature. And so that allows us to relate these two pressures since they're observed or recorded at the same temp. So we can essentially plug those values in, right? Our total pressure was 725 millimeters of mercury. We're trying to figure out the pressure of the gas. We know our H2O was 18 millimeters of mercury. And so we can solve for the pressure of the gas to be 707 millimeters of mercury. We'd want to do a conversion before going straight to the equation because of our gas law constant, right? That's in terms of atmosphere, not in terms of millimeters of mercury. So we would need to divide by 760 millimeters of mercury to get now that value in terms of atmospheres. So now we have everything to go on to step two. We have our pressure now, we have our volume, we have everything, the mass, our temperature, and the only thing that we're missing is molar mass. So we can now plug our values in. Making sure we're in atmospheres and liters. we had the 0.523 grams for our mass. Gas law constant, and our temperature was 303 Kelvin. And so that's solving for that molar mass value. So we would have, really this we could plug into our calculator as far as putting everything on the same side. Take the product of the numerator there and then divide by the product of the denominator. And so we get a value of 30.6 grams per mole for the unknown gas. So that's the idea of mixtures of gases and Dalton's law of partial pressures. And now let's get into kinetic molecular theory. And basically this just is, is a way for us to relate basically the kinetic energy of gases to molar mass and temperature. And so if we kind of look at maybe a chart here where we have in the y-axis, relative number of gas molecules, and on the y-axis we have molecular velocity. And so that's going to be in our meters per second. So we could look at these as incremental, going up by 500 meters per second. Maybe up to 3,500 meters per second. So what we, kind of find is that there isn't one direct molecular velocity for a particular gas. For instance, hydrogen has a pretty even distribution of molecular velocities going, from the beginning all the way to the end there. But as we increase, molar mass, we find that distribution, tends to not be as great. Here looking at helium. And then we could even get to looking at oxygen, just as a representative set. That we find that there's, a trend that we can see here. And that's pretty simple. The lighter the gas, the faster it actually travels. And basically answers, the age-old question of why farts travel so fast. Right? So we can start to now actually explain this conundrum, right? You know, who smelt it first, dealt it first, right, type of thing. And it really has to honestly do with this idea of molecular velocity and molar mass. We'll come back to that idea in a conclusionary statement in a little bit. The problem is that, you know, a gas has a range of molecular velocities. And so in order to compare, you know, one gas to a different gas, we use what is known as root mean square velocity. And the root mean square velocity is, you know, it's really kind of an average velocity for a gas. And basically allows us to compare velocities, namely root mean square velocities. And so our root mean square velocity has this term that looks like this. Sometimes they have the RMS there to indicate this idea of root mean square velocity. It almost looks like a square root or a funky V. And that is equal to basically the square root of 3RT over molar mass. So our T here is our temperature, and we need to have that in Kelvin. Our R value is the thermodynamic gas constant. So it's a different value. It's 8.314 joules per mole Kelvin. And we have to understand that now we're talking about, you know, kinetic models and thermodynamic models. So we're not using a gas law constant in terms of, you know, volume, temperature, moles, you know, pressure. We now have to have this joule relationship. And so that's why we have this other R value for thermodynamics involving gases. And we then have our molar mass. And that's where we tend to see an issue with students, because while we're used to grams per mole, we need to be in terms of kilograms per mole. And again, that's that relationship between the joule and the units that make, you know, up the joule, the kilogram meter squared per second squared. But all in all, it's a pretty simple equation to use to just determine the root mean square velocity of a particular gas. Some of the problems that we run into is the R value, making sure we have the thermodynamic R. And then also commonly we see the mistake in terms of molar mass. Let's do an example of this. What is the root mean square velocity of nitrogen at 25 degrees Celsius in miles per hour. So a little bit of a conversion there at the end. Only one equation do we have out here that has root mean square velocity. So we're looking at our expression for our root mean square, which would be, the square root of 3RT over our molar mass. We have our R value. Again, we want to have the thermodynamic R value. Our temperature would be 298 Kelvin. And our molar mass for nitrogen would be 0.028 kilograms per mole. Again, got to make sure that we're in kilograms for that. So we kind of have two steps here. One is just basically solving for the root mean square velocity, and then two, we're going to need to convert that meters per second to our miles per hour, just to keep our dimensional analysis practice going. So if we now plug in our values, we have 3 times our 8.314. We have our temperature, 298 Kelvin. Our molar mass, again, want to stress the units. And we end up with a root mean square velocity of 515.2 meters per second. So if we now continue on with the conversion process, right, we would just have to look up some conversions. We can start with the numerator, the meter. There's 1,610 meters for every 1 mile. So that's getting out of the meters unit. Now we're in miles per second. And then there's 3,600 seconds for every 1 hour. So now getting rid of the second value, and we're left in terms of miles per hour, or 1,152.7. And if we look at our sig figs, we're probably looking at around, 2 sig figs for this answer. So we're looking at roughly 1,200 miles per hour. So they actually travel quite fast on these gases. So that's the first type of kinetic relationship with this kinetic molecular theory. There's also Graham's law. And Graham's law basically, relates the diffusion or effusion of a gas to its molar mass. And so if we look at diffusion, basically, that's how long or how fast it takes for a gas to be evenly distributed. In a container. So if we had, let's say, a box here, and we have gas that's introduced, let's say from maybe a fart, how long does it take for us to get to that even distribution idea where we have our box but now that gas is evenly distributed around the area. And so that relates time or speed, and that's diffusion. Effusion is basically the same as diffusion, but molecular motion is restricted. This allows for better measurement. And this is basically because of how fast, since gases travel so very fast. So a little bit easier maybe to just bring in a picture of effusion, which we see here off to the right. So, in one side of the box we can introduce the gas and it starts to move around. And then the two boxes are separated by a pinhole, which we can see is, right in the middle of the box. And so that allows some of these gaseous molecules to travel to the other side. And that just slowly, reduces, or rather elongates the time for total, homogeneity. So this allows for us to make an easier measurement because of how fast these gases actually are traveling. And so there are two forms to Graham's law. It just depends on what you're being given. Are you being given a rate, or are you being given a time? So that's the two versions that we can see. And so in terms of rate, we say the rate of gas A over the rate of gas B would then be equal to the square root of the molar mass of gas B over the molar mass of gas A. And so that would be looking at rates. We also have a time version where we would say the time for gas B over the time for gas A is then equal to the square root of the molar mass of gas B over the molar mass of gas A. So that would be looking at the time version. So rate and time are related to one another, right? 1 over time is basically your rate. So that's why we see kind of this flip-flop happening between gas A and gas B as we go from rate to actual time. So it just depends on what you're given in using Graham's law. So let's look at an example of this. So our question starts with this kind of fact that it required 68 seconds for a sample of nitrogen gas to diffuse down a capillary tube, and it took 85 seconds for a second gas to do the exact same thing. Is the second gas propane or is it butane? So when I look at this question, I see that two things. A, I'm looking at diffusion. So as soon as I see that term of diffuse, I'm thinking about Graham's law. And then if I look at what's being given to me, I'm given times of 68 and 85 seconds. So I want the time version of Graham's law. So we could say that with the time version, we could say, well, the time for molecule B, which we'll say is time B, over the time for our nitrogen gas, right, would be equal then to the molar mass of gas B over the molar mass of the nitrogen gas. And both of these, my C4H10 and my C3H8, which is what we're, comparing or contrasting with the second gas, these have different molar masses. So that's how we can determine which gas it is that we can solve for the molar mass of gas B, and then figure out, is it propane or is it actually butane. So if we just plug our numbers in, right, we would have our time for B was 85 seconds. Our time for gas A, which we're calling the nitrogen, it was 68 seconds. And that would be equal to the square root of our molar masses. And so what we're trying to determine is the molar mass for that second gas, or gas B, and we know the molar mass for nitrogen is 28 grams per mole. So if we square both sides, that gets rid of the square root, and then if we multiply over our 28 grams per mole, we can solve for the molar mass of gas B, which just so happens to turn out to be 43.8 grams per mole. And this is the molar mass for propane. Butane has 4 carbons, If we had 4 carbons times the molar mass of carbon of 12 grams per mole, that means we'd have to have something for butane above 48 grams per mole. So since our value is below 48 grams per mole, we can automatically say it's propane. But you could calculate it, and that's what you would get. And so this takes us full circle to the idea of why farts travel so fast. And it's because of how light in terms of molar mass it's how light they are. If we think about, what is a fart, well, it's methane. And what other types of gases are in, a room? Well, we could say that there's nitrogen gas, there's oxygen gas, maybe CO2 gas, H2O. And if we start to compare like molar masses, we find that, nitrogen is 28 grams per mole, oxygen 32, carbon dioxide 44, H2O 18, but CH4 is actually the lightest of the bunch. And so that's why farts travel so fast. And, who smelt it first, dealt it first might not actually work because of how fast these gases actually travel or how honest somebody is in smelling it. So there we go. Some real world, real world facts, proven with Graham's law and kinetic molecular theory of gases. The last bit of this module is now looking at real gases. And so we have to remember that the ideal gas law has some assumptions. One being that molecular collisions of gases is purely elastic. And this is not true due to intermolecular forces of attraction. That, these gases, they don't just bounce off of one another. When they come in close contact, they probably hang out for a very split second because of that attractive force. We know gases have very weak forces of attraction, mostly dispersion forces of attraction, but yet there are forces of attraction. So we, are making some assumptions with the ideal gas law. And so we have what's known as the van der Waals equation. And we're not going to get too much into using this in terms of calculations, but just that we're aware of it. And so here is our expression. The right half of the equation looks very much like our ideal gas law with the nRT, but then we see these other kind of values that we see in the parentheses, namely two new values. There's what's known as the A value and the B value. The A value is a pressure correction. Due to forces of attraction, the pressure calculated using the ideal gas law is lower than what it should be. So the A value corrects for this. And that's relating this idea of forces of attraction. So you could think of A value and attraction, right, to help make that connection. The other is the B value. And this is a volume correction. Basically, due to the fact that gas molecules have their own, right, 3D volume, it means that the volume we calculate using the ideal gas law is larger than what it should be. So the B value corrects for this. And so it's correcting for the idea of molecular volume. So if we were looking at like a plot of, let's say, N here being 1 mole, then remember N here would be what? PV over RT in terms of our ideal gas law. And so if this is 0.5, 1.0, 1.5, or in terms of increasing moles here, right, we would expect our line to be, a constant going across, no matter what pressure or volume, right? If we know we have 1 mole of gas, well, then we should get this type of straight line. On the y-axis, we'll have pressure in terms of atmospheres. And what we're looking at is pretty significant pressure here. And so right here is where we would have 0. So these are all in terms of atmospheres. And so what we find is that with certain molecules, it just depends on what we get, whether we have like kind of a positive deviation or a negative deviation. Here is helium, and helium has this type of positive deviation. If we're right around atmospheric conditions, which was what we kind of see in this area, 1 atmosphere, or atmospheric conditions. It actually behaves quite like, the ideal gas law, and that's why we tend to use the ideal gas law. Is we tend to be dealing with pressures that are very, very, very small, and that's when the gas law works out very, very well. But when we start to squeeze out a lot of the empty space and go to higher and higher and higher pressure, this is where we start to see derivations occurring, and now the ideal gas law doesn't work as well. And that's why we would then use the van der Waals when we get to these units of much higher pressure. Another, say, plot would be maybe looking at here looking at methane. Or even carbon dioxide. I'll draw that one again. And so we find that it actually dips below before going up above. And so we have two different deviations. We have positive deviations, and that's what we're looking at, kind of taking that line. If I was to extend it, more, we're looking at deviations that are on the top side of that, and positive deviations come from our B value, or we have basically due to size. Size derivation. And then if we look at the bottom, we have negative deviations, or our A value. And so those are deviations going down. And so that results from the notion of our forces of attraction. So that's how we can look at these deviations, and that's really all I want us to kind of realize is that the ideal gas law really doesn't work all the time, especially when we're at levels of high pressure, and certain deviations from it occur. Positive deviations are a result of volume or size of the molecules in that B value, while negative deviations would be as a result of forces of attraction and our A value. So that's the van der Waals equation and real gases, and that is all of Module 10.